Okay, good afternoon all of you. Uh, so today actually we are going to discuss hydrocarbon reactions. We have already done the important mechanisms in this chapter, hydrocarbons, and we have also done the mechanisms, and we have also done the two important types of isomerisms, that is conformation isomerism and geometrical isomerism. And today what we are going to do is we are going to discuss some hydrocarbon reactions. Discuss the important reactions of hydrocarbons. So first of all, preparation of alkanes. So suppose there is one alkene, CH2 double bond CH2. So you react it with hydrogen and the catalyst is either platinum or palladium or nickel. Okay, CH2 double bond CH2 plus hydrogen, platinum or palladium or nickel, and temperature is 473 to 573 Kelvin. So under the circumstances you will get alkane. Like for example, the alkene is being reduced to alkane. Now for reducing the alkene we are using these catalysts. There is another option, you can use one catalyst called rainy nickel, and rainy nickel is basically that you have to take equal amount of nickel and aluminium. What is rainy nickel? You have to take equal amount of nickel and aluminium, and you will have to wash it with NaOH. Right? You will have to take equal amount of nickel and aluminium. You will have to wash it with NaOH, and after that, whatever residue is left, that residue you can store it with water or ethanol. Right? You take equal amount of nickel and aluminium, you wash it with NaOH, and the residue you store it with either water or ethanol. So that is known as rainy nickel. So rainy nickel is more reactive than nickel in this reaction. Then Okay, the second method is that if you start with either cyclohexene or hydrazine, right? If you start with either cyclohexene or hydrazine, then then what will happen is that the alkene will react with cyclohexene or hydrazine to give alkane plus aromatic compound. So in this, actually what is happening is that the alkene is receiving hydrogen from this compound. So this compound is either cyclohexene or hydrazine. So alkene is receiving hydrogen from this compound. So this reaction is also called transfer hydrogenation. So this is the alkene, this is the cyclohexene or hydrazine. After the reaction, like this compound will receive hydrogen from this compound. As a result, it will become alkane, and in turn this one will become aromatic, and aromatic is stable. So the stability of the aromatic is the driving force for this reaction, right? So transfer hydrogenation, this is method of alkene preparation number 2. Okay, the other thing is that a little while ago we discussed hydrogen plus catalyst, hydrogenation. Now in hydrogenation, one important thing has to be known, that if you have a molecule in which there is any unsaturation other than hydrocarbon unsaturation, like see, this one is a double bond that is due to the alkene, but here you have the benzene ring, so there will be double bond over there. Here you have carbonyl double bond O. So these double bonds, this one, this one, this one, will not be affected. That is another very important feature of hydrogenation, catalytic hydrogenation, that only the unsaturation due to the hydrocarbon will be affected by the catalytic hydrogenation. This benzene ring double bond O, these will not be affected. So this is reaction number 3. So reaction number 4 is that reduction of is actually from the cycloalkanes. So reaction number 4 is from cycloalkanes. So suppose you have cyclopropane, suppose you have cyclobutane. So cyclopropane H2 nickel 353, cyclobutane H2 nickel 393, they will give you alkane. Now you will notice that for cyclopropane the temperature is 353, for cyclobutane the temperature is 393. So why is the temperature different? That is because in cyclopropane molecule there is greater strain, right? Strain depends on these bond angles. So in cyclopropane the bond angle is 60, 60, 60. and cyclobutane it is 90-90-90. So there is a greater strain in this, and that is why it is being converted to the alkane at a lesser temperature. So this lesser temperature 353 is because of the greater strain. Okay, the next reaction is reduction of alkyl halide. So suppose alkyl halide plus nascent hydrogen is giving alkane plus HX. So nascent hydrogen is used to reduce the alkyl halide to alkane, right? So from where are we going to get the nascent hydrogen? So that we have to see. So alkyl halide plus nascent hydrogen is alkane plus HX. So this nascent hydrogen, how do you get it? Okay, so this nascent hydrogen, from where do we get it? So nascent hydrogen, you can get it from a certain combination of sources. You can get it from zinc plus acetic acid. You can get it from zinc plus, okay. Actually, this will be zinc plus ethanol. So you can get it from zinc plus ethanol. You can get it from zinc plus dilute HCl, zinc plus NaOH, and then there is one electrolysis in which zinc and copper are the two electrodes, and ethanol is the electrolyte. So these are the different ways in which you can get nascent hydrogen. So zinc plus ethanol, zinc plus dilute HCl, zinc plus NaOH, and zinc copper are the two electrodes, and the electrolyte is C2H5OH. So these are the different ways in which you can get nascent hydrogen. Okay. Suppose CH3 CH2 CH2 Cl or CH3 CH CH3 Cl. This is primary, this secondary. Alkyl halide can be reduced with LiLH4 to give alkane, right? So, but the condition is that this alkyl halide has to be either primary or secondary. Tertiary will not be acceptable. So, either primary or secondary alkyl halide LiLH4 will give you CH3 CH2 CH3, but tertiary will not be acceptable. Okay, suppose CH3, 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 CCl, if you reduce it with LiAlH4, okay, suppose this compound, if you reduce it with LiAlH4, then what will happen is instead of alkane, you will get alkene. So this is the reason why we cannot use LiLH4 for 3 degree alkyl halide. So for 1 degree and 2 degree, it's okay, but for 3 degree, instead of alkane, you will get alkene, that's why you cannot use it. Okay, now just like LiAlH4, there is another metallic hydride, that is NaBH4, that is also considered a suitable reducing agent. So this is the alkyl halide with NaBH4, but this is primary, you will not get any reaction. Suppose alkyl halide NaBH4, this is secondary, so you will get a product, and tertiary you will get a product. Now, so this is interesting. Just remember like this, LiLH4 will reduce primary and secondary alkyl halide but not tertiary. NaBH4 will reduce secondary, tertiary but not primary, right? Now we have another reducing agent called triphenyl tin hydride, TPH, triphenyl tin hydride. Now TPH will reduce 1 degree, 2 degree, 3 degree, everything to alkane, right? So triphenyl tin hydride will reduce all three to alkane. So that is the thing. Okay, and one more thing is that whatever reactions we have discussed regarding the alkyl halide for alkyl iodide, for alkyl iodide only for iodide, it is better to use alkyl iodide plus Hi at 420 Kelvin. For any other alkyl halide, we can use those methods, but for alkyl iodide, iodide plus Hi 420 Kelvin, this is considered the best method, only for alkyl iodide. Okay, now we come to the method of preparation of alkane from acids and carbonyl compounds. So as acid red phosphorus plus Hi will give alkane, then aldehyde red phosphorus plus Hi will give alkane, ketone red phosphorus plus Hi will give alkane, then RCOCH3 NH2NH2 will give one intermediate which sodium ethoxide 450 Kelvin will give alkane, and ketone plus zinc mercury amalgam plus concentrated HCl will give alkane. So these are the reactions how to get alkane by reduction of. By the way, this second last one and last one, they have a name. The second last one is called Wolff-Kishner, and the last one is called Clemensen. So the second last one is called Wolff-Kishner and the last one is called Clemensen. So these are the reactions. Okay, now this is called Grignard reagent RMGX. So in this Grignard reagent, this R is either alkyl or aryl, and X is either chlorine, bromine or iodine. So if you hydrolyze Grignard reagent, then you will get alkane plus a magnesium product. Now in case of water, if you use deuterium, then you will get RD. Instead of alkane, you will get alkyl group with deuterium. So essentially, the concept of Grignard reagent is that in Grignard reagent, actually the compound has got a ionic structure, and the alkyl part is the carbon ion. So you can see this is the carbon ion, the alkyl part, and then you have the magnesium part, which is the cation. And this carbon ion takes up the hydrogen, because hydrogen is in water. Hydrogen we consider is like a proton. So this carbon ion will take up the hydrogen from water to give alkane. So essentially in Grignard reagent, the reactivity is due to the ionic nature of the compound Grignard reagent. So if you have a look at this reaction, you will get an idea. So this is the Grignard reagent, this is the carbon ion part, this is the magnesium positive part, and this is the proton donating compound, and the carbon ion is taking out the proton. So you are getting this alkane, which is conjugate acid of the carbon ion, and then you are getting this one, which is a conjugate base of the proton donor. So this is the reaction. So this reaction is called protonolysis. So decarboxylation, so this is the sodium salt of carboxylic acid plus NaOH this is soda lime, and on heating is going with alkane plus Na2CO3. So this is decarboxylation, right? Now decarboxylation actually is a reaction in which the original acid has got this carbon in which the answer alkane doesn't have. So original acid has got a carbon this, but in the answer alkane that carbon is not there. So decarboxylation is kind of a step down reaction. One carbon you are getting less. But decarboxylation has got one drawback. The drawback is that sometimes you get unwanted products. So let's have a look. So this is the problem. C2H5CONa plus soda lime on heating gives C2H6 plus CH4 plus H2. So you are getting two alkanes in the answer, which you don't want. You don't want two alkanes, but you are getting it. So decarboxylation is not considered a good reaction for this reason. So this is the alkyl halide plus sodium ether, and two molecules of this alkyl halide will give a symmetrical alkane. So this is 2,5 dimethyl hexane. So this is the alkyl halide. Two molecules of this with sodium ether is giving 2,5 dimethyl hexane. Okay. Okay, the next reaction is Colby's electrolysis. So suppose you have R1CO2K plus R2CO2K. So these are potassium salt of carboxylic acid. On electrolysis, you will get the alkane R1R2 plus CO2 plus H2O plus KOH. This is what you will get. Okay, so potassium salt of carboxylic acid on electrolysis is giving alkane plus CO2 at anode and KOH plus H2 at cathode. So, in the Colby's electrolysis, it is always likely that R1 and R2 might be two different groups. Okay, it is not compulsory that R1 and R2 will be the same group. So, if R1 and R2 are two different groups, then apart from the alkane R1 R2, you will also get R1 R1 and you will also get R2 R2. Okay, now one thing perhaps it's very clear that the two methods, like out of all the methods that we have done, the two methods, Wurtz reaction and Colby's electrolysis, they are very good if you want a symmetrical alkane with even number of carbons. So these two seem to be very good. But if your answer is an unsymmetrical alkane, then Wurtz reaction and Colby's electrolysis are not very good methods. Now, if you specifically are wanting unsymmetrical alkane, then the best method is called Corey-House. That is specifically targeting unsymmetrical alkane as the product. So in Corey-House, okay, so alkyl halide reacts with lithium in presence of diethyl ether to give alkyl lithium. Okay, alkyl halide lithium diethyl ether will give alkyl lithium plus CuI will give R2CuLi, and R2CuLi with another alkyl halide, a different alkyl halide will give R dash. So this R dash is the unsymmetrical alkene we are targeting. But there is a rule. Uh, there is a rule that the second alkyl halide, that is this one, it should be either methyl or 1 degree alkyl or 2 degree cycloalkyl. So this R dash X, it should be either methyl or 1 degree alkyl or 2 degree cycloalkyl. This is compulsory. This is compulsory. It has to be methyl or 1 degree alkyl or 2 degree cycloalkyl. Otherwise, this reaction will not be successful. This one can be anything. Okay. This one can be anything. But this one has to be methyl or primary alkyl or secondary cycloalkyl. Okay, now next is hydroboration. So in hydroboration, what happens is that you have to take the alkene, you have to treat it with diborane. So after treating it with diborane, you will get trialkyl boron, and trialkyl boron with AgNO3NaOH will give you the alkane. So this method is called hydroboration. And one more thing is that instead of using a basic solution like AgNO3NaOH, instead of using a basic solution, you can also use acidic medium. So it is not compulsory that you have to use AgNO3NaOH, which is obviously basic. You can use acidic medium, then also you will get the alkane. Now, what happens is that suppose if you have a diene, like this is a monoene, it has got only one double bond. Suppose there is a diene, means there are two double bonds at two places. Then what you will have to do is, you will have to use not diborane but another borane which is very big in size. So that is called dicyamyl borane. So dicyamyl borane. So this dicyamyl borane in presence of acetic acid, what will happen is that the less substituted double bond will be converted to alkane. So there are two double bonds, one here, one here. So out of these two, this is less substituted. So the less substituted one will be converted to alkane. So dicyamyl borane is a sterically hindered borane. It's a very large size borane, and it is used to selectively reduce the less substituted double bond in a particular diene. So out of the two, this less substituted, so only that is reduced. So that completes method of preparation of alkanes. Okay, now regarding the chemical properties of alkanes. So in chemical properties, we already know very well the most important chemical property of the alkane is the halogenation under UV light. So that is the most, which we have already done last day, the free radical substitution. We have already done that. Now today what we will do is that same reaction, we will just look at it once again, and we will consider the different reactivities of the different hydrogens in that molecule. So we will just look at that. Okay, so suppose let us say that there is a alkane CH3, CH2, CH2, CH3. Now you want to do chlorination of this alkane. Okay, you are interested in doing chlorination of this alkane. Now for chlorination, the different hydrogens, their order of reactivity, tertiary greater than secondary greater than primary. So tertiary will be 5, secondary will be 3.8 and primary will be 1. Now the primary hydrogens, there are 6, 3 here, 3 here. So total there are 6. And secondary hydrogens, there are 4, 2 here, 2 here. So primary 6 and secondary hydrogens, there are 4. So if the chlorination happens over here, then the compound is A. So Cl, CH2, 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 CH3. So this compound is A, right? And if the chlorination happens over here, then we call this compound as suppose B. Now, if it is compound A, that means the chlorination is happening at primary hydrogen, and for primary the reactivity factor is 1. So 6 into 1 is 6. But if the chlorination is happening over here, this is secondary hydrogen, and for secondary the factor is 3.8. So 4 into 3.8 is 15.2. Then 6 plus 15.2, the total is 21.2. So the percentage of A in the final mixture of two compounds, the percentage of A will be 6 by 21.2 into 100, that is 28.3, and percentage of B will be 15.2 by 21.2 into 100, that is 71.7. So percentage of A is this, percentage of B is this. So this is a technique you can apply. There are similar calculations for bromination, but I will tell you honestly, those will not come. Only for chlorination, if possible, try to learn these factors. For bromination, there are similar calculations, but it will not come. Okay, next we come to isomerization. So isomerization, what happens is that AlCl3 is considered a very good catalyst for taking a straight chain alkane and getting it branched. So if you take AlCl3 at 573 Kelvin, you will get branching. You have another option. You can take AlCl3 with HCl at a different temperature like 298 Kelvin. Like for example, this alkane AlCl3 HCl 298 Kelvin. So this is a very important reaction called isomerization. It will create a branching. So aromatization, you take hexane, combination of Cr2O3, Al2O3 at 873 Kelvin. So first of all, there will be removal of 2 hydrogen, you will get cyclohexane, and then removal of 6 hydrogen to give benzene. If you take heptane, then same catalyst, Cr2O3, Al2O3, 873 Kelvin minus hydrogen, you will get methyl cyclohexane. After 6 hydrogen, you will get toluene. Right? The only reactions left in this chapter are pyrolysis and combustion. Those are really not very important because those are very mechanical reactions. There is no predictability. So that means alkanes is fully over. So I'll just rub the board and we will now start the reactions of alkenes. Okay. Now the next reaction is dehydroalization of alkyl halide. So this is the alkyl halide, this is the base, so this is the alkene, and in this alkyl halide the X part, it can be chlorine, bromine, iodine, it can be OTS, OTF, OMS and OBS. Now TS is this compound, that is toluene with a S double bond O, S double bond O. Then MS is S double bond O with methyl. TF is S double bond O with benzene and CF3, and BS is S double O benzene and Br. So these are the so these are the various combinations of X. And regarding this base, so basically this reaction is elimination. Now regarding this base, so this base is concentrated KOH in C2H5OH, and there is another combination alkoxide in alcohol. Another combination is DBN, that is diiso bicyclonone. So this base can be concentrated KOH in alcohol, alkoxide in alcohol, or DBN, diiso bicyclonone. So these are the possibilities for this base. Okay, so if it is a alkyl halide like this, then you will get 80% of more substituted product and 20% of less substituted product. So the fact that more substituted product is 80% and less substituted product is 20%, this is called Seitzef rule. Okay, the more substituted product is 80% and less substituted product is 20%. This is called Seitzef rule. So, few things. This reaction, ease of this reaction 3 degree greater than 2 degree greater than 1 degree. Then ease at which you can obtain the alkene, R2C double bond Cr2 greater than R2C double bond CHR greater than R2C double bond CH2. This one and this one have the same ease of reaction, RCH double bond CHR greater than RCH double bond CH2 greater than CH2 double bond CH2. Then trans greater than cis, okay, trans greater than cis, and cis is equivalent to this compound, like trans greater than cis, and these two are both equivalent. Then regarding the alkyl halides, RF less than RCl less than RBr less than RI. Another thing is that bulky base is preferred. Bulky base is preferred. So when you are doing this reaction, See, it's written alcoholic KOH. So alcoholic KOH is a base. So bulky base is preferred means, like say for example, ET3N will be better than alcoholic KOH, something like that. So triethylamine will be better than alcoholic KOH. So bulky base is actually preferred. Okay, the other thing is that if the final product has resonance stabilization, then that will be a more preferred product. Like this one is giving a compound with resonance stabilization, whereas this one is not. So this will be a more preferred product. So suppose this is the alkyl halide. After removal of bromine, you will get this. So if the hydrogen is removed from CH2, you will get the product X. and if the hydrogen is removed from CH3, you'll get the product Y. So obviously this will be the major product and this will be the minor product, because this one is more highly substituted. So this is called Sedzeff rule. The more highly substituted one is the major product. Another thing is that in this one you are getting cis and trans, but stable is trans, so it is major. So this is also another factor, the stability of the alkene. This is also another factor. Then if you have a hindered base triethylamine, then the Hoffman product will be major and the Sedzeff product will be minor. So that means that when the base is hindered, then the opposite happens. Sedzeff is minor and Hoffman is major. Okay. Then this is another example. Tertiary butoxide is a very large base. So Sedzef is minor and Hoffman is major. Okay, so if the base is very large, if it is a sterically hindered base like triethylamine or tertiary butoxide, only then the Hoffman product. By the way, for normal expectation, we expect Sedzef. So the other one, when it is Sedzef, the other one, the minor one is called Hoffman. So if it is a hindered base, then the major product is the Hoffman product. So here Hoffman is major and here also Hoffman is major. Okay, we have completed elimination reaction of alkenes, and to be honest, this session has extended quite a bit. So I think it will be better if we complete the rest of hydrocarbon reactions the next day. We will easily be able to do that, because I think that we have already done a very major topic today, this one. The one we did just now, that is elimination reactions of alkenes. This is a very, very important topic. So this itself is a lot of work done for today's meeting. I think it will be better we do the rest of the chapter the next day, and certainly that will be the last session of hydrocarbons. I don't think it is a realistic thing to try and finish hydrocarbons in one meeting like this. Okay, so we'll continue next session, and we will start the class with the preparation of alkenes after this one. Thanks a lot. I'll conclude this session now. Thank you. Bye.